whatever I have to say, but that means that's at least it's a very good idea to check whether maybe it's also if you make a projective assumption. Yeah. And then as soon as you've done that, you don't get claim that it's true or false. You just look at the statement. Yeah. If you say, well, I take the same statement, but instead of ellipse, I say conic. Interesting conic. Two advantages. One, it's more general. Two, it's probably easier to prove. And then if you try about thinking about proving it, then you can say, well, I choose a line which doesn't pass through the conic, and then it becomes a theorem about an ellipse. So you see it's equivalent to the original theorem. So you can go both directions. Oh yeah, very good question again. Thank you very much. So glad you mentioned this. This document here. Yeah. Boundary parallelism. I uploaded it last week, I think. Can we see a date or not? Last week, I discussed the proof of this Newton's theory. You remember? And then I got a few questions. How about other parallelograms? And I showed you in GeoGebra. And someone said, well, you claim it's obvious for circles, but I'm cleverer than you are. For me, it's even obvious for ellipses. So I worked that out to show you that this is not so terribly obvious. But also, in this document, I changed the direction. So during the lecture and in this other document, changing perspective, I usually start with the projective theorem, and then I work towards circle. Okay. Here, to show you that you can do it the other way around too, in this document we start with a very special situation. A circle inscribed in a square. That's a Euclidean or a similarity thing. It's not even affine, it's even more special than that. Yeah? Okay. So I start with a very special situation, and then I work the other way. So now, suppose I apply an arbitrary Euclidean transformation to it. Well, nothing happens. It's translated and rotated. I apply an arbitrary similarity transformation. The same thing plus scaling. Nothing interesting. I apply an arbitrary affine statement. Now things start to get interesting because the square is no longer a square, but a parallelogram. The circle is no longer a circle, but an ellipse. So it's an ellipse inscribed in a parallelogram. And what do you get? Well, you get exactly Newton's bounding parallelograms and so on. So here's the document. On purpose, I wrote it in the other direction. Now I start with a special case, and I look what happens when I apply an arbitrary transformation to it. I could have written this document the other way around too, start with and then work backwards. But just to show you that you can go both directions, this is an example where I go in the other direction. False. So here I have this statement. I have this circle in a square, and you know many properties. Yeah. And then most of them you can see them immediately. Okay. Oh, sorry. And then the question is, I apply arbitrary affine transformation. For example, you can do this in GeoGebra very easily. Making a mark. So it's this. You get something like this. So this is kind of a typical image under a typical affine transformation of this situation. So certain properties are preserved, other properties are destroyed. For example, it's obviously no longer a square and a circle, but it's still a parallelogram and an ellipse. And d prime is still the midpoint. And this is still parallel to this. And this chord is still bisected, and so on. So I have these 9 statements, most of which are preserved, but some of which are destroyed. And there are several ways to approach this. The easiest way is to look at my answers, but maybe that's not the best way to learn this, to do it yourself. Maybe you should think about this and try to This is affine, this will be preserved, this will be destroyed. Or you can look at the figure. The best way is to argue, of course, abstractly. And the next thing would be to check with the figure, and then to check my answers. And then the main question is, how many mistakes did I make? Okay, so, yeah. And here I have, just to show that analytic proofs are awful. At some point, I even gave up. I didn't want to do it, to make a stupid proof, but I can give a blank proof. Yeah? Okay. Yeah? So this is the other direction. So you can skip this. This is just to show that analytic proofs are awful. Yeah? It's just a comparison to show you that this is much better to do it this way. Yeah? Okay. Oh, Henk. Ja, dat hoeft niet centraal te doen, dat kunnen wij. Ja, vorige keer nog een vraag gekregen. Ja, als je dat kan laten zien.
Alright, okay, dat is